Thank you, and good morning, everyone. Thanks for attention. My name is Jian. I'm from NCAR. So today I'm going to give a presentation about a project I have been working on in the past 2 years. The title, as the coordinator said, is utilizing a Kokkos-based dynamical core in a Fortran-based Earth system model. So this project is a cross-organization collaborations between NSF, NCAR, University of Michigan, Texas A&M University, as well as Sandia National Lab from DOE. So for people who are not familiar with atmospheric modeling area, there's a terminology called dycore in my title. So the dynamical core, or sometimes we say dycore, it is a component in the Earth system model that solves the primitive equations for the state variables such as like wind velocity, temperature, pressure, and the densities. It usually follows the conservation law for momentum, energy, and mass. And it's a very important component for the Earth system model because it handles the grid discretizations both horizontally and vertically. It also decides the numerical methods that are used to solve a set of nonlinear differential equations. And because of that, it typically is very critical and challenging to implement the dycore because you need to worry about your numerical stabilities, its correctness, as well as scalabilities. Because of that, different organizations usually develop their own dycores. So the dycore developed at NCAR in our community atmospheric model is called CESM. It is a spectral element-based method. It is non-hydrostatic. When I say non-hydrostatic, I mean when we solve the equations, we ignore the vertical motion and acceleration calculations. Because of these assumptions, this dycore is typically thought good for simulation with coarse grid size that is larger than 20 kilometers globally. This code has been written, and for decades, it's written in Fortran. It scales really well on CPU based on our test. And as you can see at this moment, there's no GPU support for this dycore. So the dycore developed by DOE in their ESM Earth system model. It is also a spectral element-based method, but it's non-hydrostatic. That's why we call it SENH here. And by saying non-hydrostatic, it means they explicitly calculate the vertical motion and vertical acceleration. And due to that features, we think the non-hydrostatic core is really needed for a fine global grid simulations where the grid size is typically less than 10 kilometers. This dycore is written completely in C++ and the Kokkos library. They have published a lot of papers showing that it is performance portable on both CPU and GPU platforms. And also it supports various vendors' GPU, including NVIDIA, AMD, and Intel. So that motivates the project that I've been working on in the past 2 years. It is called the Storm Speed project. It is funded by the USF Foundation, and it is a 3-year project. So the technical goals of this project include, first, we wanted to integrate the SENH dycore from ESM into our CAM framework. And then after this work is done, we want to do some evaluation. We want to evaluate the performance of different dycores within the same CAM infrastructure, so make sure that it's an apple-to-apple comparison. Also, for the SENH dycore specifically, we are interested to see its performance on various GPU architectures that we have at NCAR, as well as its performance at the ultra-high resolution, which using our own CESM cannot do at this moment. One thing I want to cover, but I really want to highlight, I think it's also an important component of this conference, is that we adopt an automation of CI tests on our internal cloud server that has both CPU and GPU available. So I feel like it's really helped a lot for us to maintain our software development during the cycles. So first of all, how we migrate the SENH dycore. So to do so, we need the major 2 pieces. First, on the left column shows we need the source code. By source code, I mean we need the Kokkos source code for the SENH dycore. We also need the Fortran source code of the CAM model, obviously there. But we also need assumedly, I think the previous 2 talks have a very introduction to that you need to handle the language interoperability between C++ and Kokkos. Fortunately, DOE writes it for us for free, so we can just use it directly. That also means the major efforts of this project falls on the right-hand side, which is update our own infrastructure to handle the new code that is brought into our repo. So this includes, but not limited to, first, we add the GitHub submodules for both the Kokkos library as well as the SE/NH dycore source code. And second, in our current CAM code, we don't build a Kokkos library. So we need to decide how we're going to provide it to the users who want to test SE/NH into the CAM infrastructure. So there are two ways. We can either compile the library on the fly, or we can pre-build it with some configurations and install it as system modules. So at this moment, both options are available in the framework for users to choose based on their preference. Another challenging thing we find during the project is that our CAM model using the classic make-build system, but both the SE/NH dycore and the Kokkos library use the CMake build system. So we need to find out a way how to make those two things compatible with each other, and we are not missing any configuration setups. And although the SE/NH and SE CESM dycore both had SE there, their interface changes a little bit, so we need to handle the process interface update as well as some variable mapping stuff, so make sure that we pass the correct values to different dycores. And once the integration work is done, we also need to define some test configurations so that we can verify the scientific correctness of the SE/NH dycore in our CAM model, as well as the performance compensate that is reasonable for evaluation. So let's look at some performance setup first. So first of all, I will show you some strong scaling results of different dycores on CPUs first. So we talk about the SE CESM, we talk about the SE/NH, and interestingly, at the same time, there is an independent effort going on, which brings another non-hydrostatic dycore into CAM. It's called MPass. It's a different unstructured grid dycore, and it's also written in Fortran. So I will just show you the results for 3 dycores. So at this, in this slide, I will just focus on the coarse resolution simulation. And by saying coarse, I mean roughly about 100 kilometers resolution for SE dycore or 120 kilometers for MPass dycore. And because I'm only interested in the dycore performance, I turn off all the physics parameterization and I/O explicitly. So all the timing is only from dycore. And in terms of the architecture for the test, I first test our own supercomputer called dycore at NCAP. It is a heterogeneous machine, has both CPU and GPU nodes available. For the CPU nodes, it has 128 AMD Zen 3 CPU cores per node. For the GPU, we have 4 NVIDIA A100 GPU per node. So this is strong scaling result for 3 dycores on the CPU first. The y-axis is the maximum work clock time per time step per MPI rank. The y-axis is the number of compute nodes. So the lower value, the better performance. As you can see, all 3 dycores generally scale quite well, close to linear when we scale out to different nodes. But you can also see the green line is our CESM Fortran dycore in CAM currently, and the red line is the SE/NH dycore we brought from DOE. They are 2 times speed up, even if they are both spectral element-based method. So the naive question here will be, why? And you can probably find tons of reasons to explain why you get the 2 times speed up. First of all, I think most of people here program in C++. So you can easily argue, well, C++ is better than Fortran. That's why you see the performance improvement. And also you can see, oh, when DOE writes their dycore, they probably do a lot of code cleanup. They may allocate the memory more efficiently, use it more efficiently. Actually, they are all possible reasons, and they do happen during the design. But we talk with the developers and the staff at Sandia, and they believe the majority reason why I can see a 2 times speed up is because for the SE/NH dycore, they use a different numerical solvers, which allows them to run at a different time steps for better stability and scalability things. So here I just show you a table of different dycores. So at the beginning, all the 3 dycores use the same dynamic time step, which is 300 seconds in my case. But when they go to the detailed simulations for the detailed step, like viscosity calculation, tracer of actions, vertical remappings, the SE/NH dycore allows the model to run stably with almost 2 times larger time step. And that's the major reason why you see a 2 times performance improvement in the previous slides. So that's for the strong scaling results. Another interesting is that for our CESM dycore in CAM, traditionally, we observe a big sensitivity of the compiler choice on the CPU performance. And our experience that Intel always runs the best, and the GNU or NVIDIA will run slower. So we are interested to see for the SENH dycore, the Kokkos-based one, does it show a similar thing? So here I just show you a strong scaling results of the SENH dycore with different compilers. So different colors here refer to different compiler we test on Rachel that includes the Intel, GNU, and NVIDIA compiler. So as you can see, the red line shows the Intel runs, it runs the fastest, while the green line shows that the GNU, it runs the slowest. And if you look at the detailed difference between those data points, the difference can be as high as like 30 to 40%, which is really not small. So I want to mention that in this test, I'm just using -02 optimization levels because our model shows some wrong results when we increase to -03, so that's why we have -02. And I think I talked with some Kokkos admin teams, and I believe Harry gave a talk as well, that depends on which compiler you are using, what optimization level you are using. The vectorization done by the compiler on the back end can vary a lot. So this is an interesting topic. I expect to talk with more Kokkos developer teams to figure out what's going on here. So that's all for the CPU results. Now we look at the strong scaling results of the SENH dycore on the GPU. So one thing I want to highlight is that in order to do the GPU runs, I only need to recompile my Kokkos library backend from CPU to CUDA backend. No single line code change is needed, which I think is really nice. So the red line here shows the best CPU results with Intel compiler we see in the previous slides. The green line is the GPU results. So first of all, you can observe that the GPU doesn't really help a lot in terms of the benefit. It only shows better performance when you use like 1, 2, or 4 compute nodes. And it loses the scalability really quickly. This is actually expected because, as I said, this is a coarse grid resolutions. You don't have enough computational work to saturate the GPU at this moment. So when you scale out, you lose the scalability. And we can also plot the GPU computational time only for this simulation, which is shown as the purple color on the slides. And you can see the big gap between the green line and the purple line. That is the data transfer happening between CPU and GPU at each time step. This basically tells you for these configurations, the majority of time is not spending on the computation on GPU. It's just focusing on the data transfer between CPU and GPU. And let's say if we can develop a component set, say running everything purely on GPU, like SENH dycore is running in the DOE model right now, the purple line should be actual GPU performance we are looking for. And in this case, you can see, even if it still loses the scalability very quickly, it outperforms the CPU performance, even if we scale to 22 compute nodes. So this is a really encouraging one. So before I move on to show you some ultra-high resolution simulations, another thing, as I said in the early slides, that we are interested to see the performance portability of the Kokkos dycore on various vendors' GPU. So in these cases, we will switch from the ratio to another cluster called Casper at Anka. This is a small cluster. We don't do it for production run, but usually we do it for testing because it provides us different vendors' GPU nodes. So we can have one node of GPU node with 4 A100 GPU per node, like on the Rachel. We also have a GPU node with 4 NVIDIA H100 GPU per node. And a couple of months ago, we installed a new node which has 4 AMD MI300 APU per node. And for MI300, it has 6 SCD per APU. And you can also configure the APU in different ways, like a single partition accelerator or core partition accelerators. We want to see whether the Kokkos dycore can just run on those GPU nodes and what the performance looks like. So it turns out that it works, and once again, to get it working, the only thing I need to do is just to change the backend for different NVIDIA architecture or the AMD architectures. It's great. And the green bar here shows the performance on a single GPU node for different vendors' GPU. At the first glance, it doesn't really make sense. As you can see, the H100 GPU is running even slower than the A100 GPU node. And for the MI300 APUs, depends on what configuration you are using, the performance differs really a lot. So we further plot the computational time for those the GPU node runs. It now makes more sense. So the H100 GPU for the computational only, it's almost 2 times faster than A100 GPU node, which is something we were looking for. And for the MI300 APUs, it can be even faster, especially you configure it with the CPS configuration. So I bring this result to show to our system admin on Casper and say, hey, what's going on? And they said, yes, the reason why you see a poor overall performance of H100 GPU node is because their PCIe topology is really bad compared with the A100 GPU node. They are using a newer version of PCIe, but their switch is less efficient, so the affinity, the NUMA affinity is not handled correctly compared with A100. That's why you can see it spends more time on the data transfer. And for the MI300 APUs, this is the first time we got this APU. Nobody knows how to configure that. So we are actually happy to know, okay, we should use the CPX configuration to do the work here. And one thing I want to highlight is, for the SCNH dycore, it actually doesn't leverage the unified memory yet. So potentially in the future, if we update the source code to make sure that it recognizes the unified memory, the rightmost green bar can be very close to the purple bar here, then which will show you the great benefit of using MI300 APU in these cases. But again, a key takeaway from this slide is that to test on different vendors' GPU, we just need to change the backend of Kokkos library, which I think is really good by adopting the SCNH dycore compared with the other technology. So now we can look at the scaling performance for some ultra-high resolution. So first of all, I will show you the strong scaling result at 3.5 kilometers globally. And for these high resolutions, it's just so high, so memory intensive, it actually doesn't fit into our A100 GPU node on the ratio. So I can only show you the CPU scaling results. But as you can see, for this one, the CPU result scales almost linearly from 128 compute node up to 1024 compute node. And I want to highlight that the 1024 is almost half of our total machine capacity. So we are really excited about this result. This is probably one of the very minimum applications we can scale that well to that amount of the resources. And then we relax the resolution to a little bit to 7 kilometers so that it finally fit into our GPU nodes on the ratio. So in this case, it's the red line, the CPU result. It also scale almost linear up to 256 node. And for the GPU nodes, because right now we are really running a lot of things on the ratio, on GPU, we can saturate each GPU quite well. So the GPU scaling also looks linear in this case. You can see the green line here. And if we plot the computational time only on the GPU, it also scales close to linear. And in these cases, if we look at the computational benefit between the GPU run and the CPU run, even if we include the data transfer time, GPU achieve about 3.5 times speed up compared with the CPU runs. And if we look at the GPU computational only, it will achieve about 6 times speed up. So this is consistent with our general experience that in order to see a benefit of running things on GPU, you do need to have a large problem to saturate the GPU to make sure that you are fully utilize the resources there. So that concludes my talk. So in this presentation, I show you that we successfully integrate the SCNH dycore into our CAM Fortran framework. This Kokkos-based dycore achieves really good, strong scaling results at various resolutions. It is portable to different CPU and GPU architectures. It also supports the major compilers that we use in this community, although we see some performance sensitivities, but it's good. And also, because it allows us to run at ultra-high resolutions, it also advances our own CAM models' readiness for the modern architectures, as well as some fancy new scientific discoveries. So in terms of some future work, I show the GPU results on scaling results on A100 only. On Casper, I cannot do the scaling test, but we are working our collaborators at Texas to run it on their machine, which has Hopper GPUs and even Grace Blackwell GPUs. So hopefully, I can show you more scaling results in the future. And because of the good experience with the Kokkos dycore here, I personally is also learning Kokkos and trying to use it to rewrite our Fortran-based parameterizations. And hopefully we can run it together with the SE dycore, so not just dynamics only on the GPU. And like the two talks before said that it is possible that you can interoperate between the Kokkos and the Fortran directly. And for our physics code, we actually already have some parameterizations running on GPU with OpenACC. And recently, I just figured out that it is possible that for the Kokkos code with CUDA backend, we pass the device pointer directly to the OpenACC kernel running on GPU and getting back. There's no data transfer needed during that process. So there's a separate project I'm working on that explores that possibilities. But we can have more updates in the future about these things. So with that, I want to thank you the funding support from the NSF for this project, as well the computing resources support from NSF. Also want to thank John from Anka and Luca from Sandia. They are not officially on this project, but help a lot about the code implementations as well as the performance evaluations. Here's some reference about the dycore referred in this talk. And with that, I will say thank you for your attention and happy to answer any questions.
We have time for 1 or 2 questions while the next speaker is setting up.
When you compared the compiler performance, did you set the floating point model explicitly for Intel compiler? Because like Intel really likes to do that implicitly, setting whatever.
Oh, I'm sorry, I missed the last part. Can you repeat it again?
So in contrast to GCC and Clang, the Intel compiler by default sets floating point model too fast, which corresponds to to unsafe math or whatever oftentimes. So if you want to have a fair comparison, you should set it to stable or something. I don't know if you did. That was the question.
That's good. Yeah, I don't think I said that explicitly. That's a good thing to test.
Right.
Thank you for the suggestion. Yeah.
We have time for 1 more question if we have 1 more. No. Let's thank the speaker again.